psychology. That is, it, its essence really, in essence, really, the theory of relativity accepts the pre-relativity mechanics of Newton's mass and Maxwell charges and magnets views, but now takes into consideration the fact that light is used to observe the world, unlike Galileo. Really, it is divided into two major cases: linear motion, which is based on inertia, no force of any kind in SR, and nonlinear motion or force in GR question mark. Einstein uses partial differential equations, which is part of advanced calculus or even tensor calculus, let alone that they are tensors. These are simply vectors in a coordinate system plus a transformation equation to another second coordinate system, and the mathematics is complex and methods exist only for some of these equations, especially nonlinear partial differential equations. These are solved by using numerical approximation methods on computers, but Einstein said that in an exact analytical solution to these field equations, so need an advance in mathematics. And also he said that need to define the energy tensor of matter, which appears in the field equations, and he could not do it. So he said because of our ignorance of the laws of distribution of charges inside matter. So we need an advance in physics. Relativity considers perception, since both observers use light to observe the world and is the same speed for both of them. But if light speed is affected by the relative speed, then it is negligible anyway, since objects move far slower than the speed of light. So it is a good approximation. They show that even the speed is not fast enough to affect the speed of light in the Michelson-Morley experiment. So really, if the experiment is valid, if our eyes cannot detect such a minor fringe shift is needed, is it valid? The following is a summary of the general theory of relativity after studying it for about 35 years. Case 1, SR1. When the object is at rest, not moving relative to you, then your perception of it is like that of the perception rather than at rest relative to it, and the major result is equals mc squared. Use classical mechanics of Newton and classical electromagnetism of Maxwell to derive the laws of motion of SR, and then remove the parts in the equation due to motion. Really, time may be still distorted in that you don't know a planet or a star existence is far away, and light from it didn't get to you, or may have passed your point long ago. Case 2, SR2, just compares your perception of an observer of an object that is moving under no force in a linear fashion, inertia alone, a force applied before and removed, relative to you, to the perception of an observer of the same object by someone who is stationary relative to the object. Case 3, SR3, just compares your perception as an observer of an object that is moving under no force in a linear fashion, inertia alone, a force applied before and removed, relative to you, to the perception of an observer of that same object by someone who is also moving under no force in a linear fashion on the same path but with a different speed, inertia alone, relative to the same object. So SR applies to both of your perceptions of the same object, and you just relate your perception to his perception. Case 4, for the general theory of relativity, GR just compares your perception as an observer of an object that is moving under a force, have curvature of revolution or rotation, and possibly inertia to the perception of an observer of the same object by someone who is stationary or moving but not accelerating, or no curvature relative to that object. That is, SR applies to the other observer, but is more complex in your case. Maybe it covers both cases of objects curving in orbit around you and object curving away from you as well. Case 5. Did Einstein discuss the question mark? GR2 just compares your perception as an observer of an object that is relatively accelerating to you, i.e. it is moving under a force, have curvature of revolution or rotation, or you are moving under a force, and possibly there is inertia to the perception of the same object by someone who is also relatively accelerating by a different degree of acceleration relative to the object. Is this a more complex theory than general relativity? Question mark. Indeed, long ago they gave a prize to someone for someone to describe the theory of relativity in a few sentences, and Einstein said that he could not do it! Exclamation mark.